Hello and welcome to Barkland Labs. This is the pre-lab for the skateboard video, or the skateboard lab, which is a friction lab. We're going to be looking at how friction differs between a tile floor and a carpet floor. So, down here we've got something called a force plate. That's basically just a scale, like a bathroom scale that you might have, and it actually hooks up with a Logger Pro so that we can find the mass of an object. So for example, if we put a few of these 1 kilogram masses on there, it would tell us that how many newtons of force those objects are pushing down on that force plate with. Another thing we have in this lab is the force sensor. So let's see if I can put it right in front of here. It's called a dual range force sensor. You'll notice that there's a setting of plus or minus 10 newtons and plus or minus 50 newtons. What that is that measures different ranges of force. So if you're going to do a lab that involves relatively small amounts of force, you want to use the 10 newton setting. So maybe if we're just pulling blocks around, which we will do. If you're pulling people around, you're probably going to be using the 50 newton range. Basically, it'll help you be more precise with the measurements that you're using on each of those. Maybe the most important thing about not safety, but not wrecking lab equipment has to do with this cord right here. We are going to be pulling people on skateboards while you are holding this force sensor. What you don't want to do is ever hold on to the cord as you are pulling. This is not just an electrical cord, it's also sends and receives data to and from the computer, and if you pull on it at all, it will sever those cords and it will not work anymore. There's no way to fix it once it happens. I had some students do that a couple years ago. These things cost about $125 a piece. I think you do not want to ruin that part of it. The fact that it's a dual range force sensor is because you can push up here, or you could pull down on that hook and it's going to register force either way. Okay, so that's a little bit about how the components in this lab work. So with the force plate down here, right here, the first thing you need to do is you actually need to choose somebody in your group that wants to weigh themselves. Not everybody has to do this in this lab unless you really want to, but the reason I want you to weigh yourself is you need to figure out what your gravitational force downwards is. That's basically the amount of mass that's being accelerated by gravity down. And then what we're going to do is we are going to pull this skateboard with a person on it, and you're going to see how much force it requires to pull them on two different surfaces, the tile floor and then out in the hallway with the carpet. Next part to show you about how this works is how we're going to pull. We've got a piece of string here that you are going to, get this out of the way, you are going to put underneath. I'm not a skateboard person, so I don't know what these terms are. The axle, maybe, right here. And you want to be careful that it's not getting caught up in the wheels at all, otherwise it'll get tangled and it's not going to pull very well. And so then you put this down, your person gets on the skateboard. So these cubes are representing the mass of the person on there, and I'm going to bring this over here now. So now when you're conducting this lab, what you're going to do is you want to pull as perfectly straightforward as possible with no side to side, or even more importantly, you don't want to pull up or down. You want to pull perfectly forward and level. What you're going to do is you're going to pull just enough to get the person going, and then you want to pull them along at a constant rate for as long as possible. So what you're essentially measuring is how much force it takes to just start them moving, and then how much force does it take to keep them moving at some constant velocity. The key here is that velocity needs to be constant. It doesn't actually matter what the velocity is. What you should remember from our PhET lab is that to keep them going at a constant velocity means that they're not accelerating, so that force that you're pulling them forward at should be the same as the amount of friction that is working against them. I'm going to show you this from the side as well. So once again, they're stopped right now. I exert just enough force. Oops, and this whole time I have been using the force meter. So you hook this on here. Now remember, you're pulling it with here, you're not pulling it from the cord. So you're going to pull very slowly with just enough force to just get it moving. And then you want to keep it going at some constant velocity as best as you can. So what you're going to find is how much force is required to keep this moving at a constant velocity, and that should equal the amount of frictional force that's working back that way. So once again, the amount of force you're pulling this way should equal the amount of frictional force pulling that way if you can get an acceleration of 0 or no speed change. Okay, the next part I'm going to show you is how we analyze this on the computer. The Skateboard Lab video, and I'm going to use a FET application to show you both what's happening in the real world plus what's happening on the graph to kind of connect part 1 and part 3. So we've got this guy here who is kind of like the moving man, except for he's going to be applying a force on this crate. And I want you to watch this graph as he's pushing on here, and I also want you to look at the arrows as he's pushing here. So you can see the force of friction and the force of acceleration that he's applying are equal. And then as soon as he successfully pushes it, notice that that force of friction goes down. Okay, I'm going to go ahead and clear that and rewind it. Let's get the box back over here and clear that. Okay, so once again, I'm applying force. Both arrows are getting bigger and bigger and bigger and bigger until all of a sudden it comes into motion, and I can decrease how much force I'm applying to keep a constant amount of velocity, because I don't want it to accelerate. I want to go the same speed. And what you should look at is this graph. If I zoom in here, oops, a little bit too far. If I zoom in, you'll notice it took me a lot of force until a total of, I can't read that, maybe 600 newtons of force before it started moving. That's called static friction. That's how much to just get it moving. And then you notice to keep it moving, this pretty consistent line right here, that's known as rolling friction. That's how much force needs to be applied to keep an object in motion, not to accelerate it, just to keep it traveling at a constant velocity. So if we go back to a picture here, on Logger Pro, on the next part of the video, I'm going to show you how we get a graph that looks something like this. Static friction is how much force it takes to just get it moving, and then the rolling friction, it should look somewhat-ish level, and that's how much force to keep it going at a constant velocity. Okay, in this video, I am talking about how to use Logger Pro to measure the frictional force applied on a carpet or tile floor. So you've got Logger Pro open. The first thing you want to do is go to Experiment and 0. Actually, hold on, let me just open this up brand new to show you guys how this works. So you might notice that it says 1.15 newtons of force are being exerted right now. You can go to Experiment 0. You want that as close to 0 as possible. It might fluctuate a little bit, but if you're not applying any force, you don't want it to read as giving off any force. The other thing is we don't care about the negatives, so you can click down here, make the lowest 0, and you'll probably be able to adjust this too once you wait until after you do your first trial to see what you might want to do that for, possibly. And the other thing you might want to do is collect for a longer amount of time. Go to the data collection up here and collection duration of 15 seconds. Okay, so now we are ready to collect. I've got my hook on the string. I am on the plus or minus 50 newtons one on this one because I'm pulling. Actually, I'm going to go to 10. Oops. So I just changed it to 10 newtons because I'm pulling some weights on a skateboard. You will probably want to be on the 50 newton setting, at least when you're on the carpet, because you're pulling a person. They weigh a lot more than these 5 kilograms. So now you're going to go ahead and hit collect, and you're going to start pulling that until it just starts moving, and then you want to keep it moving at that constant velocity. Okay, so that is pretty good there. So I'm going to go ahead and go up here. I can probably make it go to 10. Another thing you can do is you can actually auto scale if you want. Sorry about that. Oh, no problem. You can go to auto scale, and that will the computer decides how it looks for you. Okay, so you should have something here where you get a big spike, and then it lowers down. It should look relatively constant now here at this point. You can click on the Examine tool, and you'll see that the amount of force it took me to just get the skateboard moving was about 7.5 newtons. Just like in the terminal velocity lab, you probably want to give this a much larger font so you can actually read it. So yeah, it took about 7.5 newtons to just get the skateboard moving, and then once it was moving, you notice it took a lot less to keep it moving. You're going to want to do multiple trials of this to see what that amount of force is to keep it at about a constant velocity. If you draw a line through maybe kind of through the middle of here, you notice it takes about 3.4 maybe newtons to see where I'm putting my cursor back and forth. That seems to be about the middle point that it takes to keep it moving. That's the rolling frictional force to keep that skateboard moving. So let's go ahead and try that again and see if we get consistent numbers. We should get 7.5 newtons and about 3.4-ish newtons if we're doing this well. Okay, so collect, and I'm pulling it, and okay, I think I screwed this one up. Let's go ahead and try that again. So, oops, I just ran out of the cord. So I'm looking at the examine tool, and that time it only took about 5.5 newtons to get it started, so that's less. This is why we do repeated trials, make sure I didn't do something wrong that first time. And you'll notice that constant rate, again, was maybe somewhere right around 3.4 newtons or so to get it to keep on going. This spike right here is when it ran into the cord, actually. Let's go ahead and do a few more trials. So, okay, to get that started, I'm going to keep it going at a constant velocity. So examine tool, okay, 7.3 newtons to start it, and then all of this kind of nice and level stuff right around here, about 3.4 newtons. Again, this is when I had to pull it because it was almost stopped for a second. So I know it's a little bit confusing to analyze, but we're looking for that first big spike where the static frictional force is, and you're looking for a nice plateau where the rolling friction is, how much it takes to keep it going. So we're doing this lab hopefully on Tuesday, and I hope that helps you.